Okay. Thank you again for being here today. So let's start directly with the business. So last time, so we're about to define this analytic prismatization. We're trying to do some study properties of it. The last thing we did was introduce this category. Of upfront curves. That just to recall, so an object in this category basically triples where S some perfected space in characteristic P. We have a suitable important thickening, maybe nil thickening of the initial, well, maybe Y0 infinity construction of S, so this localization of the vectors of this one, and some kind of Frobenius on this method here that was compatible with the Frobenius concept. So this was the replacement of our category of delta rings in the setup of this analytic prismatization. So this category, we also have the category of these near perfected rings over QP. Again, was some kind of generalization of semi-perfected rings or P-complete rings, and that basically were used to set up the geometry of all the objects appearing in the analytic prismatization. And out of this, we could finally construct the category of, let's say, stacks that would be involved in the construction. This we have the category of, call it the free stacks, but again, there is a hidden topology point. So it was very well renamed, so it's nice. This one is just free shifts of these new preparatory spaces. Again, just objects built up from these rings, for example, in rigid space, fit into this setup. Or again, it's modular taking some suitable simplification. And also, using this category, we could define some basically category of stacks in Partington curves, analog to the category of stacks in the rings. That maybe let me just call it. So these boards, I'm going to just write down all these budgets. Going to everywhere, so this one I just appreciate that. Perfecto is P. These are the category of, let's say, nice or presentable stacks. This one be the category of Partington stacks. Or generalized non-compact stacks. Okay. So out of this, again, similar to delta rings, we have a forgetful functor from delta rings to just rings, P-complete rings, and we have some right adjoints given by big vectors. So of these big vectors prismatization used to compute precisely the geometry of this prismatic homology. So in this case, the replacement of that, or maybe just the avatar of that construction, will be given by suitable left adjoints between this category. So we have just a forgetful functor from F from this category of frequent stacks into this category of nice stacks. Just again, we have some analytic stack that is representable by these rings at least, and map all from these rings to this stack, and you can just forget the structure. Look at analytic stack, forgetting all the stacks that we put in here. So this functor extends extension, basically it's a polemic preserving extension with all these right here. So now our lemma. This guy has a left adjoint that I'm going to just denote that, like the Y construction. This being stacks nice. This category of stacks. Stacks. And well, it's a left adjoint we commute with colimits. So I just need to tell you what happens for these imperfected guys. It sends imperfected to an object that we just called y like S, and it's going to be the initial curve to which S maps in this category. So quickly, this guy push out. Given by, well, the first thing you do is you take just the reduction of the curve, which is a perfect space. You take it field, then you define the curve. Here you have an on-field, which is a divisor, and you want to make this continuous equivariant. Just like move around all this. This one again does not to a bunch of copies of Zagger. You end up with the shot. So try to just compute what is the initial object in this category that which stack maps is precisely this one. So basically, again, like this left adjoint is going to be our version of bit vectors in the setup, and something that we discussed time. Actually, you can rebuild these constructions out from bit vectors.
Sorry, what's the left vertical?
Sorry, this is, well, you have an inclusion from S bar to this, and then you just take all the Frobenius twist of this inclusion. This is just the push out of the element. Right. So I'm going to that. Even S. Perfectoid. So curve. With a map. This is just the initial part of the map. Okay, so the next goal in order to define the prismatization was to make a notion of deep one, right? The notion of deep.
So, have you proved the lemma, or are you?
I'm just going to, I mean,
You're not.
I'm going to prove the lemma, but also it's not too hard just for the
okay. So it's okay. No.
clarify this. This is supposed to be analogous to the adjunction, like if you were working with the classical rings, the adjunction between delta rings and
beat
whether
vectors.
they're
Yes. This is exactly the analog of that, and
So this is an analog of what?
for taking beat vectors.
Which vectors is the right and showing?
Yes, in the right
We are dealing with space.
Exactly. Yes. So bit vector is the right adjoint at the level of rings, which turns out to be the left adjoint at the level of spaces. And again, like something information last time is that you can actually concretely build up this one out from certain localization of bit vectors of the underlying ring of this class. Right. So now the definition of the force of bit one. So definition. So for first, let some kind of generalized fractal picture here. So a degree and D can define a divisor. This thing is just a Cartier divisor, meaning again, this guy has the structure of a adic space in this more general sense. We still can talk about asymptotic immersions given by just locally one ideal. So this makes sense in terms of geometry. And the condition is that if you take the full part just to the reduced part of the curve, now we have a Cartier divisor in an actual like Carpenter curve of a wise infinity construction attached to a perfect space. So this one be in YS bar. And again, this notion makes sense thanks to I would say Bourgeois and Fontaine, where they study the case of divisors of these curves at different points and prove out they set out the foundations of this part of the theory, and then taking up more families, maybe develop functions. So this notion is just a notion that you test at the level of geometric points. And at the level of geometric points, all these spaces are essentially curves in the sense that you can cover by actual principal ideal domains. And then you can just define this notion of degree at the level of points.
So the question. So what is the problem? Is the problem to define the notion of divisor or the notion of degree of divisor?
Of degree of divisor.
Of degree of divisor.
Yes.
And you are saying that in order to do this, you can pass from YS theta to Y.
Yes. So essentially, the reason is because here you're taking some kind of reduction, and the degree of a divisor should only depend on the reduction of the scheme, essentially the reduction of the space. And now in this case, we have just a families of curves that is parameterized by the geometric points of this one, and we can just use the geometric points to define the degree of the divisor. Well, maybe these two works actually say that actually this makes sense. So this is the degree of the divisor.
Why Y S or
Sorry?
Y S or
I just put a name. Oh, sorry, why S bar?
yeah.
Yeah. I mean, the thing is that this is just an thickening of S. Yeah, these are really misleading because
The Y S bar, which is the
actually the name may be flats everywhere. Right, like the datum of this is some kind of perfect characteristic P, and this one is actually the reduction of the.
Is it? Because you have to the right above the far. The right. You have
Sorry, just
even more to the right, like basically in the middle of the chorus. Yeah, above this process of that, where we have written Fark Fontaine and Fark Schultz.
Yes.
Yeah, and above this you have Y
Ah,
as bar.
I'm sorry. I mean, I just mean.
Yes, that's what I was.
Sorry. Let me just forget that. Okay. And now we can define if B. We stack. Guys. Where basically imagine this guy evaluated one of these guys is just of the greedy device. We point to the infinity group point of all these three devices. Okay. B. So now we have we already defined the degree divisor. Now we can construct some maps. Map that takes one of these nice prestacks of this map, something like the completed version of the diamond. This is what this map is basically coding here. This category of content prestacks of bit one that just sends a space to well, morally we're taking a completed version of a diamond. So we're going to evaluate this in one of these curves. This is a data here that's determined by just these gadgets, and these gadgets is given by the degree one device of the. And as you can imagine, this is so similarly as for the case of the tilt. So usually the tilt, you take a vertical space characteristic P, and you define the tilt in the vertical space as first the possible on tilts that corresponds to these degree one divisors, and then the points of X in these possible. So here they do exactly the same angle. The language of the prismatization, where you're taking the category of delta rings, you take just a prismatic structure or Cartesian device with the vectors, and you're just evaluating the scheme in the quotient of the basically just in the device here. Yeah, it's completely that. Now definition. So the prismatization function. Composite. Again, we start with some specs. We go to these nothing, then we work with specs. If one apply this completed diamond functor, and then we just forget the structure, start to see this stuff, right? Just okay, so let us try to code, de-encode what this actually means, maybe more down to terms. So again, well, you can try to first evaluate what happens if these guys have some imperfect weight, which are kind of the object here in this category. Then, well, the first thing to do is, of course, just yeah, do it just for the final object, which is the let's take this. So this one is kind of by definition the same as one. Again, because it's the final object in this category, these functors are going to preserve final limits. Addition with that. All these functors are going to preserve final limits by definition. Follows for product from definition.
Will it preserve all limits?
Sorry?
Will it preserve all limits?
I think this one, yeah, maybe. This one, once you pass to the actual simplification, may not. Yeah, so here, let's see, of course, to actually get the correct stacks, there is a hidden simplification that I have not yet done, but that is kind of the last step when you're doing this, to identify the objects and to have enough descent.
So are you saying that prismatization doesn't compute?
I mean,
It's okay, just
I'm saying that this is a little bit subtle to say.
at least it's not clear.
Yes. And the problem is mostly because of simplification. This is what causes problems.
Is it already true for the drum stack?
It's already true for the wrong side. Yeah, yes. But before simplification, everything presents limits. After simplification,
But at least does compute finite limits.
yeah, finite limits is because this is built up of a category with like all finite limits, and let's say this would not be. Okay. So by definition, then this thing evaluated as some near perpetuated dagger just the group point of all the Cartesian divisors of this guy. This something that we're going to compute at the end of actually what this guy looks like from that definition. And maybe what is more important is what you can think about the utilization of an attribute space or general X. Let's say now let the dagger be given over this guy. That basically corresponds to a device like that. So again, this one is a great thing that we construct from a push out. And this is just a V1 device when it's a push out. And for the prismatization, this point over this is precisely given by X. So maybe to give a even more complete example, let me just make a move of prismatization.
So the question was, how do you describe the prismatization of the point? Yes, of the
just the point. And well, this is what it is. Like it's difficult to. I mean, I think it's possible to write it down more explicitly with these vectors, but it will be easier to compute afterwards once you have a set of the theory. But at least if you have given with some pixel divisor, then this one is slightly more computable, and this is one going to explain now. At least this one. So let us fix I don't know, for example, some C or P, a perfect field. Then we have a map. from well, the perfecto to the prismatization of this guy by just the from a map from just a divisor defined by some C in this pattern can keep it flat. We can just take a map from this calculus. Basically, on one opposite here, you give by this divisor, and this one is naturally this. So we can't treat pullbacks. So compensation relative to what is flat given by this thing. Just kind of fixed sort of prism, but corresponds to one divisor, and we're just looking pullback of displacement to look at relative versus the distance. So in that case, let us start with a ring. In perfectoid ring. And something I mentioned is that from this ring, we can actually consider some funny version of the vectors of this. We can do the elements of norm less equal to 1 of this ring. We can take elements of norm less equal to 1 of the perfect reduction. And the kernel of this guy is going to be just the bit vectors of the nearby had because it's a Q vector space, is just a product of what's a space construction in between them? That corresponds to if was just some kind of pullback, and here you got the funny version prime this so it was a funny construction involved with this pullback, and somehow the reason why we want to from this pullback, so secretly what we're trying to do is just to make a deperfected version of the some version of a complete prismatization. So basically, for example, know that this map is also obtained by just taking limit by opinions of this one. So the only difference of this construction you take limit by opinions of this one. That is maybe one of the motivations to try to the first motivation that we had to construct this was well, taking the usual prismatization, which is by simply bit vectors, and make it perfect in a decomplete way. So this limit is just here. You can somehow do something in between that just perfectize the side which is complete and you leave the other one as it is. So I wanted to say is that this prismatization flat evaluated at the ring R is going to be given by Gibson at this funny version of bit vectors. After you mod out by a suitable lift of this element C that is given by this close point, of course, right? Here, and of course, maybe you want vector B because you have vector 0. So again, like this construction that corresponds to just take the degree 1 divisor and something like that is can also be studied or write down explicitly the setup just by taking these versions of bit vectors. So, but the reason basically is because this object, which is this YS dagger, is constructed as just a localization of these bit vectors. If you take an analytic spectrum, these funny bit vectors, and then, well, you invert something like it. And you just remove politically the locus for the suitable leaf for the diagonal vanishes. This construction is just the same as his funny push out. Again, this push out that maybe geometrically is just easier to better, but that turns out to be the same as this sort of localization of vectors. And any such quotient like that is going to factor through this open space. The end, if you just care about these quotients, it's not to actually look at this.
But I ask you a question about it. So you said there's a map from YC flat to the prismatization of QB.
Yes.
Yes, I didn't. Sorry, so I'm just
Yes.
unwinding the definition over there. Why is it coming from YC flat and not
Right.
YC?
A priori, you have this map. This map is adjoint to well, a map from YC flat to big one. Like the data of this map is basically giving you a degree 1 divisor of this curve. And then you can apply again the Lagrange trick. And basically what it's telling you is because after this, the other adjunction, the adjunction we get from the progressive function from this one to this one, we get a natural lift of this guy to this function, just by forgetting this structure.
Okay, so just a basic question here. So is the map from YC flat to so this prismatization has a Frobenius endomorphism? Is that
The
right?
prismatization has a Frobenius endomorphism, yes, because all these categories has Frobenius endomorphism.
And the map from YC flat to the prismatization is Frobenius endomorphism.
Exactly, basically correct. Yes.
So this is analogous to like an analogy and sort of performance schemes would be that you have a map. If you have like an integral protector thing like Lucy, you have a Frobenius equivariant map from both of AN to ZP.
Yes.
So this is an analog.
Exactly the same thing. Yes. Okay, so now, well, we have defined subject. Of course, this subject is interesting as long as you can say something about that. So let's start the geometry of this. So in order to study the geometry of this guy, as we have mentioned in the last talks, well, generically, this guy is going to be the RAM stack. So in order to, or maybe a better way to actually relate with this with the drum stack, it's maybe better to first try to look at this category. So in this category of Farfontaine curves, we already have some reduced objects given by just the usual curves of perfectors. And well, this provides some nice, some important interactions between these completed diamonds and the actual notion of diamonds. Again, sort of a completion of that, I suggest. So that curve P is a category vector spaces. P. Then for category, we have a natural fully faithful map. This one, essentially also given by the curve, into the category of funny. Yeah, maybe the Y0 infinity. So we can restrict a shifter from these ones to a shifter from these ones. So again, let me write a little bit more optimization. Second. So well, this is where sorry for the bunch of notation, but otherwise I don't know why this thing is sorry. So well, we have this category of perfectors, we can just reduce, or let me call you know, perfect stacks. Be again free sheets. Perfectoids. Again, we just want to compare with the usual stacks, the usual stacks. But there are just too many different geometries we need to train. This one. So again, we have a restriction factor. That I'm going to call the tilt. This category of Farfontaine stacks. This category of just perfect. That well, it's basically just an object with a restriction to perfectly spaces. And you can just use that, and you can restrict the category of perfect space. So this functor has actually got left and right adjoints. So the left adjoint is basically just a natural inclusion you get from one to the other. So it's kind of just taking another like curve. Takes a perfectoid, then we call it just S. Map to the curve S, and just extend the colimits in the whole thing. And also has a right adjoint. Right. And the right adjoint, I'm going to call it which extension. And some sort of RAM stack here. This one, what does is sends a object in here, just to the to make all the forward. One points in one of these funny curves are just the same as T evaluated in the underlying S. So you can imagine the reason why it's called the RAM stack is because this functor is independent of the thickening, only depends on the reduction. Similarly, as we define the RAM stack, you basically just take a functor and we evaluate it in its reduction.
I don't understand just synthetically what that. No, T goes to what?
This goes to this line.
Why T goes to something which is called YT dera.
Yes.
And then what's the role of YS delta?
This is just taking what the values is.
Okay. So here's the suggestion. So don't compare things this way. So why don't you just say the T? There is a functor T goes to YT dera, where YT dera of functor is
Okay. Right. This is just so maybe let me just write here we define so there is some kind of field functor. Define stacks. Stacks. This one has both left adjoint.
What's happening, so perfect pre-stacks are, is a full subcategory of FF tilde pre-stacks, is that right?
Yes.
Corresponding to the things that are dagger node.
Which are the reduced, yes.
Yeah.
So let me give an example of how this functor does and what is sort of encoding this functor by taking just one of these new example. If take something like an object in this category. So we have the object in the middle. And well, we can also just forget the structure and see as analytics stack. And the map on the left, what it's doing is just, well, this object has a reduction, which is just the underlying Carpenter cube of the perfect ring. And this corresponds to the counit of the model. So the part corresponding to the left adjoint. That's why this notation is kind of listed here. And the right functor coming from the, again, the unit of its adjunction, coming from this right adjoint, is precisely the ground stack. This one, the reduction or vision. This one is going to be the pretty ground stack. Of this guy, the same as the negative ground stack of this guy. maybe second example, this. So, so let X be a real space. Then, well, you have the usual field, which again is just an object in the category of V stacks on for spaces. So, in particular, is an object here. Yep.
This diagram.
Yes, so that's why I put this name. So maybe I should have a so I should have sorry. You're right. I should have written more details with this. So you have this diagram, and you can take this guy, and it's tilt, which is the first contour you define here. This is the underlying space size. Then, well, this diagram tells you that there is an adjunction between these guys. So there is an adjunction. T something in here. You have an adjunction between the tilt, the curve of the tilt, and it's the round stuff. Just coming from again the fact that this one is a left one. Here, because the tilt of this space is just S itself, then this sequence that you get from these adjunctions consists precisely on the reduction of the scheme of this space, and it's associated with the round stack. Well, you have a second example here. So it needs a restack of each space. Space. Then, well, we have the usual definition of the diamond. So this category of mapping from perpetual rings. And then this adjunction, well, imagine if you have this funny diamond that is precisely the functor well, constructed from this one tilt of this guy is diamond here. So what you end up getting at the end is some sequence like that. You have this, you have the curve of the diamond, then we have the round stuff. And again, what we wanted to do, and or at least one part of the heuristics behind the theory was that this corresponds to morally like ESG continuous representations. This is corresponds to the array. This one corresponds to the continuous. But again, continuous versus non-generative. And so, I mean, again, this is more like an analogy of this here, but and these heuristics between these three sorts of representation theories will going to be reflected in this trivialization of the space using this sort of language. So or all these spaces have some underlying topological space. For example, this one, so topological space coming from curves. Something that we mentioned time before is that this kind of the round stacks localize this topology. So underlying topological space is all these three gadgets here are basically different versions of different kind of analytic stacks associated to this topological space. So all of them leave over this have the same topological space. Okay, so this is kind of the okay. Language because okay. So automation of the routers. So well, we call that the space leaps over the interval 0 infinity. You got, and well, at a political space, there is inclusion. This version. On the line political space of the diamond is just basically a rigid space, it's just the underlying political space of the rigid space inside this curve. Again, and maybe this one is given by the object X itself.
Low side, not low.
Okay, so
It's singular, no?
yeah, singular.
I just wanted to ask how many of these low.
I mean, yeah, it's only one. Sorry, because it's very big one, but very big one. I'm sorry, it's only one, but it's very big. So very noble for us. And whenever we start with space, we have a closed perspective here given by this Dixon field, and over here we have this topological space. And as Akio said, this prismatization is going to be endowed with a Frobenius because of the category we're working. So we can start looking at the Frobenius inverses of different political space. Then, if we look at the complement of all these guys, basically what we want to prove that as long as we are like far from the Frobenius minus of all these points, we just get the Ram stars. U, this process. U.
You said we get the Germans checks again, plural, not the.
Yes, so what I mean is that we just, okay. Maybe I just that's up to us because I mean they're taking the Ram stars of all these guys, but it's not just to be the same Ram star. Yeah, maybe meant that the Ram star, all of them are the same. So the map coming from this the diamond, or secretly in the prismatization that again has the same underlying stack. So this one has a little bit more structure. Mapping to written the restriction below is huge. Then by complement for these points, mapping to here. Restricted view. This is
So is you said there's a map to the underlying topological space. Is that not an isomorphism?
from the Ram stack to this topological space?
Yes.
No, it's not.
Oh.
Yeah, we're in case of complete like in complex varieties it is, but we are really geometry. In this case, this is not an small.
So even though so you have y sub x diamond, that's a bar content for x diamond.
Yes.
And then you have a Saron stack, and then you have this x diamond tilde or prismatization and
Yes.
and even though these are all the same on perfectoids, these are well sort of deperfection.
Yes, these are different, like analytic, the different structures you can put in kind of the same topological space. Similarly, as whenever you have this parity group, you can have the same topological space with different functions coming from the continuous representation theory, local analytic representation theory, and like smooth representation theory. So this is some kind of another more geometric version of what's happening in these yes.
Just to clarify, those maps are not isomorphisms on topological basis, but it's the analysis, I guess they.
These ones?
Oh,
These ones?
yeah.
All of them use isomorphism in topological spaces.
Oh.
But judging underlying topological spaces, nothing more than that.
Oh, I'm sorry. So when you drew that map, if you put parentheses, if you put absolute values around both sides, that would be. Sorry, I'm just sort of.
Yes, so okay. So sorry. What I mean by this is that all these three gadgets have the same topological space, but you actually have an honest map of stacks in here, and this all these topological spaces that are the same, and you actually have an honest map of stacks in here that allows you to localize by taking just pullback of an open place.
Thank you.
Sorry. So this is the claim. We want to prove it. That again, generically, this thing just looks like a fact. So for this, again, like looking at this or this as topological spaces, so it basically as underlying stacks is right. To prove this equivalence is enough to do is a level of the line stacks, so we can just evaluate in near perfectness. Let us take this near perfectness. Then, well, again, what is something like that? So we just remove the Frobenius E process of the load side that is defined with X. So this basically corresponds to all these divisors in this curve, a map of X, but such that the I should have explained first what the Frobenius is. How this Frobenius given a point is diamond, which is the same as having this divisor. So the Frobenius of this point going to be given by the fullback by Frobenius. We are actually just given that the fullbacks are like this. So, well, what does that mean? That a math is dagger going to express answer in like the underlying topological space. Again, all of them are different. So this means that this degree one divisor stagger well, this means that you're looking those degree divisors such that the same underlying topological space of this thing, but again, it's going to be an on-tilt of this one, same as this one. So then if you de-encode what it means to land precisely in the locus supported by the X itself, so you can do it at level of diamonds. So basically, this means that you have the same on-tilt as you have of these. But these are the level of topological spaces. Having the same on-tilt means precisely that you have these equality spaces. So these points dagger, so basically again corresponds all these divisors, or at least those that are going to map into here. All these guys here, up to X, such that well, we want that eventually when we apply some Frobenius of the divisor, we do not end up in X. So this means Frobenius pullback is going from 0 to S or N. Basically, if you write this means French infinity point, you have the dagger and all the continuous translate left. So this basically would mean that this divisor is going to be just supported in this case. Of this divisor D. Again, because this is the only points where you actually modify the curves, this kind of Frobenius translates of S. This divisor is going to factor through the reduction. So basically, this would mean that the value of the prismatization in this locus of these guys is just the same as the prismatization of this locus, the point S bar, again, because this one is going to factor in here, and this is just this one side. So there it's the same as. So a little bit, sorry, maybe not here what to say, but essentially, what keep on this is that because of all these universal kind of Hartmann cubes look, just by modifying this locus, whenever you pick divisors that are not supported in this locus, this one is going to depend on the reduced part of the curve. You are not touching any nearby from here. That's in particular, like on the in this locus, the complement of this one, which by kind of duality you get from this construction, corresponds to this Frobenius minus translate of the curve. You are just going to see this Hodge state, sorry, the drum locus.
Sorry, so just to clarify, what you're saying that, so you want to evaluate, like you want to consider these sort of thickenings of classical Fresnel curves,
Yes.
but the thickening is only happening on this sort of special loci. So away from that, there.
What I want to say is that a priori the thickness could appear everywhere, but you can always find covers. So maybe you can always evaluate at these ones that are going like to cover all the other ones, and these ones only occur in this Frobenius translates of S. So basically, that is the only part where something different from the thing we already know is happening. Now maybe let's just focus on what happened. These points, what happened in these points is precisely what is that. So then there is
Wait, I was just gonna say, it is probably time for break.
correct. Okay.
Do you think that would be?
Yeah, I think that's what so. Okay, so you just have the kind of describe the locus, the gram locus, which is essentially everything but some Frobenius translate of just the topological space on X. So now we will discuss the yes. So look at the object. So one in this category of stacks as a universal divisor. Right, the one that is a full pattern of all mouse. So class and connected stacks. This produces a well, this is going to produce a map from the analytic spectrum of the representation of this A1 1 here. So let me say explicitly how this map can go. Maybe even here on the map, stagger to this one. So this map equivalent. So like the pullback of this universal divisor curve. But also by construction, if we come up from this gradient here, taking the pullback of this guy, get some divisor, which is well, precisely the map to A1 mod GM. But here, this is going to produce this map here. Um, Start. Whoop. Well, we have say X, one of these stacks. Well, we have the prismatization of P mapping to A1 mod GM. We have the zero section that is stable. Yeah, so we have this GM here. And okay, this gives you the stack P. Again, if you just go back to the prismatization, you end up with the Hodge stack. Again, it's essentially the same definition that you find in the info probability, which is well, given the pigmentation of the P, you will have some natural divisor on the line stack, which given by again. Move back to the adjunction of the ring to the B vectors, with the B vectors of the ring. And well, basically look at the locus where this divisor vanishes to take full back. Geometrically, this is you look at all divisors. This from B to Y still that. Here again, you have another closed stack. What you're asking is that you can just fill this diagram here. What you're asking me to have. So somehow that this one gets maybe study this watch state stack. Before studying the watch state stack of QP, that would be a little bit more subtle. Let us just take a relative situation at least and try to find the structure of stack, this kind of relative structure of the watch state stack of the fine line, which again is going to encode this germ structure in smooth region spaces. So again, we just fix C. Here the bracket close, just perfect. And again, I'm not C to unexpected. That again leaves come up with that. Corresponding to the device. So, so relative visualization. Fine lines C. Value this one over here. Yep. relative of this diagram. So it's an extension. The thing is that you actually have a map GA itself.
So relative means that you so in principle the Hodge state of step of GA is the step GA
Hodge state is the step over this one.
a step over QP
Yes.
but QPHT so it's complicated. You take the point of this QPHT and compute the fiber with this.
Yes. Yes. Let me please.
Wait,
Just take the pullback of the Hodge state diagram to this.
but just to clarify, is this also the same thing as taking GA tensor, like GA base change to C, and then taking the absolute Hodge state stack of that?
I think it is.
Okay.
Yes, I think it is. Yeah. This one, yes. Yes. Let me write it like that. Yes. So we have a quotient, G just G itself. Similarly, what happened for that optimization, and the kernel of this is now this funny overconvergent neighborhood of zero, G dagger, with a twist that's coming from the cartel device. One. Sure. Again, maybe let me take our imperfect ring. Just want to start up. So we want to evaluate this Hodge state stack. So this guy. So we called the Hodge state stack. First is that this object, the construction, times for this by just taking the corresponding the instruction for that. And here we have the divisor C, given by C, the pullback given to us the divisor in this guy that we're going to evaluate. This one is whatever GA could state of this guy did this. So again, this is just the same as the global sections of I should have to just
Wait, sorry. GAHT relative C, right?
relative procedures. Yes, but well, we have a factorization from S to D dagger. So this is the data that we are in the Hodge state stack. We have this one is a closed size, closed immersion of this. So this produces map from the global sections of B plus rejection to the global sections of S dagger which is just R. So basically, we just constructed this one here. Now, what we are going to compute is precisely the kernel of this. What we call how this guy is built up. So this guy is built up as some push out of the reduced fraction of the curve along some convenience translation of the reduced version of these guys along copies of these. So the level of rings, this means that the ring by this guy is just a private product. The level of rings. So certainly up is just up. Sorry, this guy is just a functions of the reduced guy over the functions of the reduced one in here, but it's a product of a direct sum because this point at disjoint is just the same. It's exactly product. Here you get the functions. So so then know that this divisor B admits we supported by hypothesis. This diagram must be here. So if we look at underlying topological spaces, these two guys have the same topological space. Because again, the reduction is just a degree one divisor corresponding to some until vertically. And these two guys have the same reduction. That is only one until of it's the same until. And again, like this one, what we did was just move around all these Frobenius translates. So when we look at what O of D is, well, this is the same as just taking O as dagger and mod out by this element L that we take pullback from C, which, or we can, again, it's just a full complex, so we can just take the full complex in each of these terms of the prime product. But in most of them, except at n equal to 0, this is going to vanish. So this is the same as with the complex of these products. But the locus of S joined the locus of Frobenius S for n greater than 0. So, well, because the element C was giving you something supported precisely in this locus, it's going to kill whatever all the other Frobenius translations. So this thing is the same as this quotient, but again, this quotient is just a degree one divisor of the reduced things, which is just the O S bar. This function again is killing all but one. And this quotient here you're doing something different. It's going to kill all of the probability translates of this bar except for itself.
That's different copies of this S bar and the Y S bar were.
The different copies were embedded in different places. Yes, the different copies were embedded in different translation properties here. But as you can see here, C is 0 in O of S bar. So if you project and well, of course, you can write this as maybe I should just say that but here what you get is
That's why you can just shape it.
essentially this sort of here. But they probably didn't like to stay here because it looks like it's split, but it should not be split.
Sorry, still be in left, the right.
Sorry? I think there is something like here. Right, okay, good.
So because this psi is equal to 0, this derived portion is going to be the thing and the
Yes,
thing
yes,
in-
yes.
in the
Sorry for the beginning.
one, right?
Yes, I think I wanted to write something
Just like making people.
yes. Let me rewrite this again. So we're going to have that. Something that is true is that this function is going to kill all the objects there. So we look what's happening in the reduction. This one what we'll see. We'll end up map at least to the reduction here. And well, I want to say is that the kernel of this markup will correspond to the near radical of this. Here you have a quotient given by just the reduction of this ring. You want to kill site everywhere. And here you have the near radical of this, that is just a bunch of products of near radicals. Stagger. So this quotient here is degree 1 divisor, so this one is just for star. This is what you want to compute. And in this one, because of the Frobenius translates, all of the terms but the terms equal to 0 is going to survive. So this thing just full complex. Here, this is one all this 0. Right? And this case, oh, we get just this one is actually 0 here by division there. Just get one and shift the one. In total, if you look at what happened at this complex, well, you have the map from O B, that is this one. Say that you can project to just GA, which was the ring R. And what this map is telling us is, well, the map to R basically just corresponds to these two pieces together, like this one and this one. The kernel of this map is precisely the piece that you can here. One beside this GA. So it's GA diagram. This precisely. Again, well, this computation is kind of an analog to the one of bit vectors. But again, we are kind of exposing a different fact, maybe more like the geometry of these objects to compute well, precisely this extension of the consciousness. So, as a corollary,
Yes, so it's quite a nice fact. So here is question. So we have a great theory which produces such things. But one would like to have a kind of more direct. So the theorem says that this is an extension. But it would be
Yes.
better to say which particular extension you get. Well, of course, you can ask what is extension. There are two cases. Number one is that this data thing is slightly. So we have an extension of GA by the twisted by let me disregard the piece and twist of
yeah.
we have an extension of GA by GA shifted by GA dagger shifted by. Now GA is a very classic. The GA dagger is not quite classical, but it's a projective kind of countable projectively, countable intersection of countable many disks. So it's still more or less understood. So we have an extension of something understandable by something almost understandable. Now, of course, one can also ask, what does extension mean? Well, you can make some guesses, but anyway, it's this theorem is crying for an improvement. I'd like to have a direct description of this extension, and especially maybe another remark is that GA is not merely a ring stack, but not merely a group stack, but a ring stack. So this extension should also be stack.
Well, I mean, I guess it has to be because it's, I mean, this is coming from the passing code, right? And this is coming from the passing code.
It's what?
I mean, this, sorry, so the fact that, I mean, this is the, I mean, this is supposed to be coming from like the passing code setting. Like, this should be maybe a different in the setting, but.
Okay, anyway, one would like to have a description of this remarkable extension without going through all this theory which involved various limits, a lot of limits. Now, this is especially interesting because we have this Cartier tool. Well, we have another picture, a parallel picture, which is potentially Cartier tool to this,
Yes.
which is being developed by
Barnard.
I mean, and again, there is some remarkable features which they construct on the picture, and it should live. It lives in a quite different world, but in order to define it, you have to use something with the effect of Francis Scholz and also recent improvement theory by so again we have the puzzle, and this is the dual puzzle. Now there is, as you pointed out, all this is parallel to the usual prismatization story, but there, more or less by definition, we know what state stack of one is. It's just the code of, it's just the following thing. We have W with vectors, and we have a morphism from W to W. Namely, multiplication by VF1. And then you take the code this morphism. So this morphism is a quasi-ideal W, and code is a big step. And then when you look at the kernel and the kernel of location of VF1, you immediately see that you get an expansion as GA by GA sharp twisted by, and this is this should be a parallel statement, and here one would like to have a similar description. Probably somebody is called as code of an explicit.
But this in this relative setting,
Yes.
At least I don't know. I would say that at least this construction that is pushed out and sort of complete, because this corresponds just to taking a product of like this extension of this print by this thing. So what is maybe not clear from that is the relation with the usual watch test.
Now, just one more remark. There is a story which you didn't emphasize. It's an important story. So actually, the whole theory started with another approach, which was explained in Scholz's lecture given last summer. The lecture is the recording of the lecture is available, but the quality is absolutely problems. So and according to what was said in this lecture, the recipe for computing this extension seems to be as following. you have to take the again, there is a construction at the level of formal skills that should you have those parts. Maybe you could,
Yes.
maybe you can explain this construction because there are still, I think it's more understandable, probably it gives some sense in answer to my question.
Okay.
Anyway, so the important fact of life is that there was another approach to the theory, which the idea was that if you want to compute the prismatization, let's say, after as a rigid analytic space. In other words, when you are in a more classical state setting, then the recipes of flows you represent. So let's say a symbol. Then you represent this, space, the generic profile of the formal scheme, and compute this, and then compute the integration of the formal scheme. And then, well, in this particular case, the watch takes spare the formal scheme, then you perfect it in some sense. And then you have, but then you have to prove independence of the truth. Choice of the performance model, and also you have to prove the construction local in the sense of choice. For equivalence, you have to prove that if you have a non-system of performance is then it uses this and here is the recipe for the watch tape step. You first take the specification of the formal scheme. Then you take and this specification carries the property. Then you take the reflective limit with respect to Frobenius, which is but objective limit in what sense? No, in what's the order of things? Limits. Just a moment. Do we first take the limit and then do something with it, or do we
First, do something with it. We look at this object as an analytic stack just by taking realization, simply complete rings.
No, so do we first pass to Frobenius, or do we first pass to generic fibers?
We first pass to Frobenius and then to
This is yes. So then this is so then this projective limit with respect to Frobenius is already defined. I'm sure that this order. So I think the objective limit that we are here is a pretty formal.
yes. So then we right. This should be a feedback arm. Limit 300, right? Yes. Limit papers. by Frobenius. No, so this is what we want to write. No, but this is what the thing is that this limit is not taken in the category of P-complete schemes, but just taken in the category of analytic types instead. So this is not complete.
Okay, so it's I would say, but most probably this means that it's limited in quotation marks. So it's just notation, like a proportion somewhere.
Mhm.
So my hope is that what you get by this construction is a proportion, is a projective limit of rather classical analytic steps. And then you just have to consider the corresponding proposition. In other words, definitions just not to pass to any kind of limit, but just to consider this projective system itself with the convention that when you want when you define a morphism from one projective system to another, then so to say there is shifts. So this would be so again. So here some details. But this would be a description which looks more understandable to me, at least as a starting. Maybe probably there are good reasons why we abandoned this approach and passed to the more sophisticated one with stuff. And one of the reasons I think he said that he wanted to work with to define prismatization of analytic spaces without finiteness.
Yes.
But at least, but anyway, in the case of rigid analytic spaces and the third update, one would like to have something understandable. Okay, so we have a plenty of puzzles here. We can consider this as good.
Maybe just to finish, as you said, this was the starting point of the presentation. Maybe just to tell a bit why we end up with these kind of definitions. So taking these kind of limits, if you translate what happens at the level of points, corresponds to taking limits of bit vectors. Right. The thing is that, of course, you take limit of bit vectors.
Maybe sorry, I forgot to say
Yes.
one more thing. There is one more subtlety here that, of course, so as I said, in the framework of prismatization, for the formal scheme, the Hodge state corresponds to the Hodge state. The Hodge state stack of Van Dyck corresponds to the code of the multiplication by F1.
Yes.
In the but notice that F1 is not reserved by Frobenius.
Yes.
So in order to get this, you have to actually first find a bit vector whose
Frobenius is
image
V1.
under Frobenius is F1.
Yes.
Now the word find should be probably understood here in quotation marks. So of course, you can in some sense find it, especially if you don't insist on getting precisely the one, but actually it's enough that you get a v of some. And then if you understand it this way, that then you can literally find. And even if you so actually it's so we what you need is to find a root vector. Instead of we have one, we can take any with vector which is primitive degree 1 and with the property that the zeroth component of the vector is 0. And then when finding the image of the Frobenius, finding a image of the nth power of Frobenius means finding a weak vector whose finding a weak vector x such that the zeros component of f to the power of n of x is
You want us to take the f roots of p of 1.
yes, and equivalent with this means the zero component of f to the power of n x is also called the nth used component. So you need a unique vector whose n used component is 0 and just in some sense generic enough. So the first usual component should be 1. Okay. And that's very, if you, and there is an explicit formula for the nth used. So this the problem is of course so but there is this procedure. So anyway, there are many puzzles in this talk and in the talk by Dart, the two collections of puzzles have this continued to each other, and probably eventually the puzzles will be so.
Maybe
by request to all the people and potential future speakers, when you give talks, don't conceal the puzzles unless you know that he will be punished for exhibiting the puzzles. It's better to tell. For instance, if you're looking for a job and if in a particular situation, maybe you will not get a job. It's the solve problems, then it's better not to. But otherwise, it's better to. Okay, so would you like to say?
I think that maybe it's a good time to finish.
Very good.
Thank you. Well, of course, maybe want to thank you for the invitation these 2 weeks, for making weeks here to discuss with a lot of people with these talks. I actually very delighted of being here. So thank you so much.
Thank you for your talks. The section I were brought up at Gelsen seminar, where there were much more interruptions by Gelsen than we So this somewhat explains. Other questions, comments?
So in the theorem, this fact is also closely related to, the theorem about the structure of the relative conjugate stack. This is also closely related to the, I guess, Fuchs's theorem about homology of it for.
Right. Right. So, yes, so the question of Arthur was if this structure of the Hodge state stack was related to the Hodge state homology you get from the Proetal side of Oakland, the Hodge state you get from Schultz's theorem. Yes, and as I mentioned before, given X, it's a British space, you have this funny tilt, the curve of the actual tilt, and the parameter here that what we know. So you can realize this as high stacks of this shape. And when you apply this functor, you end up with this object as analytic stack, with prismatization. Maybe let me proceed. And when you took the pullback of this Hodge space stack, the actual diamond of X, maybe the only of the diamond, so basically this is given by X with this O hat vector bundle. So the one corresponding to the Proetal side with O hat coefficients is going to map to the Hodge state stack here. And well, so to speaking, using, for instance, well, maybe abstract nonsense of geometric set theory, you can prove that, well, basically the cohomology of this stack, which is the same as the O hat cohomology, the usual cohomology, coincides with the cohomology of this. The cohomology of this one is precisely computed in this J component. So, modulo proving that have some kind of equivalent in the vector bundles things. The set operators appear in previous talks that appear you construct as objects in this side actually come thanks to this structure as a germ. So yes, there is a recognition that corresponds.
So just to clarify, so the statement is that the X diamond, over basically
Yes,
C and X Hodge state that they have the same cohomology. So I guess that this requires some.
Yeah, that requires some argument, of course. And well, let's say that morally speaking, the argument is coming from trying to exhibit this as best as you can, and geometric set theory. That this is a possible argument.
And this is the stacky approach to the geometric set theory that you explained in the
Exactly.
number two.
Exactly. Yes.
Other questions or comments?
I can.
Okay, so the question was how this business is going to relate to Figure module somehow, essentially. So maybe the question you raised is how to compute things like maybe G prism or the prismatization of P, or maybe GM prism. Well, we say that to compute these two guys, way to do it using that theory is well, using analogs of manifold spaces. So one of the reasons why we developed this complicated theory of I don't know, this kind of general hyperpotent curves was, for example, to be able to talk about Banach Kolmogorov spaces such that you could compute this gadget similar to as happened for the theory of diamonds in terms of them. And maybe for this one, well, you can compute it in a similar way that involves the one parameter group. there is kind of similar construction from some GM up to that, and you can play similar roles and try to make this computation. So let me talk about these two cases where you have.
So what you were talking about my one-dimensional.
I think it's
the article which was called a formal group.
I'm talking about the dual.
Group, the duals, well. But the paper to look at is the unique paper of mine, which has the words formal group and the time.
Yes. Paper when you describe this group using deep filters. So for this one, say that the key points is well, recall that for diamonds. Like big one of S period P is given by what? Well, you have the Farfronten curves, and you look at the degree one divisor that doesn't vanish. So this is the same as BC of 1 and 0 modulo the units of BC of. So it turns out that we have the same in this theory. So you have two Banach faces, BC of 1 for Analytic, that turns out to be just a limit of generic fibers of just the formal multiplicative group. And another Banach space is your O, which is just QP of open analytic. So if you believe in the same formula in this equation, for the spectrum of QP prism, again, should be computed as just the Banach of 1 divided by this. And maybe again, this would be some kind of perfect version to this phi, kind of enough to compute this. And this one, well, you can just write down what it is. This, you remove the 0, which means remove the 1, and when you mod out by the action of the units in here, which is cross. So well, here you have something like a variable in a formal open disk. So here you have something as a variable. And you have all the Frobenius limits, so all the roots of P. QPLA, you're written as a copy of this. And let's say by bookkeeping explicitly what this action gives us, this guy is going to act as Frobenius on T. Maybe T is the variable of GM. And this guy is just going to act as T to the K. And well, this is kind of the same formulas you get from the theory of T modules. Then maybe T is going to be something like 1 cross X. X is actually just a variable of Z you want to know.
So P of T is not T to the P.
Right. This say that this is one of the advantages to have of this framework is that you actually can compute these relatively explicitly in terms of things that are not too far from bridge spaces. Let me say that I don't know how to compute this without using at least these Banach spaces in this theory. Yeah, it would be a good question to see if you can actually maybe trying to make a definition like the one that we discussed before, like in terms of the limit of Frobenius of the usual prismatization. If you can end up with this sort of quotient, static quotient of the prismatization of QP, just let's say using the theory formal schemes. That would be a good question. At least we know how to compute it and if.
So just to clarify, that type of formula was in the context is a decompletion, is some sort of decompletion of an existing
Yes.
existing result for diamonds.
Yes, so in diamonds it's actually the formula I have here.
Yes. Okay.
And the formula, well, basically, the person here, you just complete, just take production, you just pass the diamonds. This one exactly is the formula for like the diamond of QP. This one is again, as I could say, just the completion, and in the spirit of this prismatization and locally analytic the completion of the formula of a diamond.
You have some version of like Iran homology. This would be like a perfect version of it, right?
That's a good question. Yes, that's a good question. So you may say that, well, you have this mapping to the prismatization. So here you could take like, the limit of this object. P. And then you can, well, I don't know, define the stack. I don't know. P or something like this, so for the names. And oh, here is the variable here, so it was a T. And you could just talk about prismatization relative to this pullback. Basically, you take prismatization, you take the pullback here. And this could be thought as an analog, so to say, of Hydron prism.
Something more like a perfect.
Yeah, it would be like a perfect version of that. But the point is that the prismatization generically uses the RAM stack. So you know this perfect version, you basically know the problem. At least you get this.
Okay, other questions? Let's say this picture. Let me, so